Thank you. All right. Well, let's all take a deep breath because I need a deep breath. What a day. Well, happy Friday to you. I apologize for getting started late. I didn't explain things clearly enough as I was doing office hours, and you should have seen the number of times somebody had to say, Dr. Price, you're not actually sharing your screen with us, and so on. So anyway, I apologize for being late. We have been talking about how to tell whether a nucleophile is a strong nucleophile or not. And when we last met, I was mentioning how asking whether something is a good nucleophile or not is the same as asking is its conjugate acid a weak acid or not. An example that we did together was to consider the equilibrium between hydronium and water and HCl and chloride. And we talked about identifying the acids on either side of the equation and the bases on either side of the equation. We talked about identifying the conjugate acid of our base and the conjugate base of our acid. And in a lot of ways, asking which is more reactive, water versus chloride, is the same as asking which is less acidic, hydronium versus HCl. And that's the same as asking which has higher energy or less stable highest occupied molecular orbital. Okay, all of those questions are similar. Now, you probably learned in general chemistry to think about acid strength with a number called Pka. If you don't remember that, don't worry too much. We're going to talk about where it comes from. But it's a measure of acid strength, and the lower the pKa number is, the stronger the acid is. So if we looked up from a table, and your book has a number of these at the back of the book and also in chapter 2, we would find that the pKa of HCl is, and I always get this wrong, somewhere between -7 and -9. I can't remember what I said. We'll just go with -7 because that's in my notes. I don't have you memorize most pKa values. So don't worry if I get the pKa for HCl wrong. I do ask you to memorize the pKa value for hydronium and closely related molecules, and the number there to remember is -2. So if you compare those two numbers, you would conclude that hydronium is about 100,000 times less acidic than HCl. Okay, so water is our weaker, H3O plus is our weaker acid. HCl is our stronger acid. And what that means is that Cl minus is our more stable conjugate base. Water is our less stable base. This is all relative, comparing them to each other. If water is less stable than Cl minus, that means water is more reactive, and therefore that the lone pair electrons on water are higher in energy than lone pair electrons on Cl minus. Okay? Should I say that again? Questions?
Yeah, can you repeat that?
Yeah. pKa data tell us that HCl is the stronger acid than H3O plus. Okay? And in equilibria, stronger acid gets to give up its proton to the base. All right, so if HCl is the stronger acid than H3O+, that also means that Cl- is the more stable conjugate base. Those two things go hand in hand, right? Strong acids, and this is another principle that you'll need to become comfortable with. Strong acids have very stable conjugate bases. In fact, that's how we're going to rationalize acidity in the first place. We're going to say that strong acids are strong because their conjugate bases are very stable. Okay? So if HCl is the stronger acid, that means Cl- is the weaker, more stable conjugate base. If H3O+ is the weaker acid, that means its conjugate base, water, is less stable and more reactive than Cl-. Okay? Now, some of you have asked, as we've learned to identify HOMO versus LUMO, what if a molecule has multiple lone pair electrons in it? How do you know which one is more reactive? And in a lot of ways, this comes down to exactly the question we've just been looking at. Which lone pairs are more reactive, the ones on chloride or the ones on water? And we would conclude from pKa data at least that the ones on water are more reactive. Okay? Questions? All right. Okay. Now, we haven't talked at all about why Cl- is more stable than water in terms of its lone pair electrons. But we will. Go ahead.
Less stability equals higher reactivity.
Less stability equals higher in energy equals more reactive. Okay. So yeah, some synonyms. More stable, lower in energy, less reactive. They don't exactly mean the same thing, but for our purposes, we can use them interchangeably. Yeah. Yeah, and some people get a little bit mixed up because in chemistry, lower in energy does mean more stable. If you get confused about that, just think about gravity, and you've got lower potential energy here on the first floor than you do up on the fourth floor. All right. Other questions? So, somebody asked, well, if you had to choose in a molecule like this, I'm just making stuff up at this point. There's lone pairs on the nitrogen, there's lone pairs on the oxygen. Which is the HOMO? Well, first of all, I'm not going to ask you that HOMO-LUMO question. But you could answer it with using the same principles we've just talked about. I might ask you which of these two groups is more basic, or which is the most reactive. And the way you could tell this is by simply considering their conjugate acids. What would it look like if the oxygen here with its lone pair reacted with an acid and got protonated? We would have a molecule like this. And the pKa for that protonated alcohol is about the same as it is for hydronium. It's about -2. In contrast, what if we had the other thing react? Lone pair electrons on the nitrogen react with an acid to pick up a proton. This resulting ion, cation, is called an ammonium ion. You don't need to know that or memorize it, but I will use the term ammonium in the class, and so just for your purposes to know what it is, that's a positively charged nitrogen that's attached to 4 different things. I happen to know that the pKa of that positively charged nitrogen is around 11. Okay, so which of the two things, this is actually called an oxonium ion versus ammonium ion, which is more acidic based on pKa information? And this is another thing you should work on and be good at. Lower pKa is stronger or weaker acid? Stronger, right. Okay, so that means the oxonium is stronger. Oxonium is the stronger acid. That means what about the conjugate base? Which conjugate base is more reactive? Which conjugate base is less stable? Which conjugate base has higher energy electrons? The NH2, yep. This will be our stronger, less stable, more reactive base or nucleophile, and its HOMO will be higher in energy. Okay? So if you had to look at that, what is the HOMO of the molecule? Well, goodness, you've got multiple things going on there. But if I made you pick which lone pair was the most reactive one, you could use pKa data to get that information. At this stage, I suppose it might be useful to figure out why we know. I mean, you can look at pKa trends, but memorizing numbers is not that useful in today's world. If the robots take over and become our overlords and deny us access to Wikipedia and the internet, then memorizing numbers will become useful again. But right now it is not. And so what we really want to do is develop a qualitative sense for why the numbers are the way they are, so that we can predict and understand how reactions happen without, even if we can't look up information. That being said, your exam will always, it's an open book exam, so you can always go look up pKa's, right? Okay. So in this case, why do you think the lone pair is less stable, more reactive on nitrogen versus oxygen? I think I heard the word. You want to say it louder? Electronegativity. Okay. That is a useful principle that can help us distinguish which lone pairs are higher in energy. Oxygen is more electronegative. Nitrogen is less electronegative. Okay. Well, hold on. What the heck does electronegativity mean anyway?
Tendency to attract electrons.
Tendency to attract electrons. Okay. Why would electrons be attracted to one element versus another? Charisma? Some je ne sais quoi? I can't speak French. Go ahead.
If I remember right, it's two factors: how close the lowest the bonding orbital is to the nucleus and the
Okay.
charge of the nucleus.
Okay, it has to do with the charge of the nucleus and how close the valence orbitals and valence electrons are to the nucleus. Good. So why would the electrons be closer to the nucleus in fluorine than they would be, say, in carbon?
Fluorine's more massive.
Fluorine has a nucleus that has more charge, right? And there's this concept called nuclear shielding. Basically, we ignore the core electrons, and then we ask the valence electrons here in this second row, what charge does each valence electron experience, and if you're fluorine, you experience way more protons than you do if you're, say, lithium, okay? So electronegative elements like fluorine, and the trend is really fascinating. If you go boron, carbon, nitrogen, oxygen, fluorine, we decrease in atomic size. We increase in nuclear charge. We increase in electronegativity, and we decrease in the energy of lone pair electrons. Okay? And this is actually fascinating. You can think of, you wanted a way to rank lone pairs on heteroatoms. Within the same row of the periodic table, electronegativity is your friend because you can interpret electronegativity as what is the energy level of the lone pair. So if we were to make an energy diagram and say, okay, if I had a lone pair on carbon versus a lone pair on nitrogen versus a lone pair on oxygen versus a lone pair on fluorine, that's what I would see. And that's all in this region of non-bonded orbitals. That's still all higher in energy than, say, a sigma bonding orbital or even a pi bonding orbital would be. But that's what electronegativity does. It moves the energy of the electrons down, okay? So we can use electronegativity to rationalize trends in pKa. Questions? So it turns out electronegativity doesn't always get you the right answer. Though, just to drive home the point, if you measure pKa's for the following acids, and we'll draw the conjugate bases that would result. Okay. The pKa trends within the first row of the periodic table follow this electronegativity trend very well. The pKa of a carbon-hydrogen sigma bond, as in methane, is like 50. That means it is, if you think about how acidic hydronium is, 52 orders of magnitude less acidic. So that means that basically if you had a group of methane molecules, all of them in the universe with all of the water molecules, water molecules in the universe, it would never happen that methane would give up its proton to water. Okay, just really not acidic. But you go one step over and get slightly more electronegative rather, and the pKa drops to like 28. And then for water, the pKa is 16. And then for HF, the pKa is like 4. All right? So electronegativity makes a big difference. Go ahead.
So would we be okay in saying that the more electronegative the atom is, the better base that, or the weaker the base is?
Yes.
So that it's not going to be as reactive?
That's right. You could, you'd be just fine saying within this row of the periodic table, the more electronegative, the less basic that atom would be with the lone pair on it. Okay? And when you're thinking about acidity, we're always going to try to draw the conjugate base and rationalize it, right? We can say that HF is more reactive as an acid than methane because when HF loses its protons, the electrons that were left behind are left behind on a very electronegative atom. In contrast, when methane loses its proton, those electrons that are left behind are on carbon, which is not particularly electronegative. So we would say that F minus is a way, every time I say F minus, I think that sounds like a horrible grade, right? We don't have F minus at BYU, so we only have, I don't think there's even an E minus, is there? No. Okay, anyway, that's not funny. You guys don't think it's funny at this stage because we still have an exam to go and you're all still very scared. So I will try not to mention those things in the future. But yeah, F minus is way more stable than the negatively charged methane. Okay? Now, sometimes electronegativity can lead you astray, but not because the principles have changed. Because remember, the whole reason electronegativity works is because we're thinking about the amount of nuclear charge that valence electrons experience. Okay, so I'm going to take you down a column of the periodic table. We'll go HF, HCl, HBr, and HI. And I'm going to sort of make up these numbers. Let me see if we can, I don't have them somewhere. So I'm going to guess HF is about 4, HCl is -7, HBr is -9, and HI is -11. Okay, let's draw the conjugate bases so we can rationalize stability of the conjugate base. I will tell you that actually fluorine is more electronegative than iodide. In fact, there is actually not a huge difference in electronegativity between iodide and hydrogen. All right? But nevertheless, of this comparison, HF is the least acidic and HI is the most acidic. Huh. So let's think about what's going on here. There's a second principle at play. Do you remember how we spent all this precious class time at the beginning talking about second derivatives of wave functions only to show that electrons that are more spread out have lower kinetic energy and are therefore more stable? What do you know about atomic size as you go down the column of the periodic table? It's bigger, right? Atomic radius increases. So I minus is the largest, whereas F minus is the smallest. Okay? That means that for I minus, the valence electrons are more spread out and therefore have lower kinetic energy and are therefore more stable. So it turns out I minus is a more stable conjugate base than F minus is. Even though electronegativity is different. It turns out we will only use electronegativity as a comparison within the same row of the table because size doesn't change that much within the same row of the periodic table. It does change, and fluorine F minus is smaller, fluorine is smaller than carbon, but the change isn't huge. In contrast, as you go from fluorine to chlorine to bromine to iodine, the size increases dramatically, and the spreading out of the electron density wins there. All right. There is another way of thinking about it, and that is that a principle that's mentioned in your MO study guide, that when you mix two orbitals together to make an MO, a molecular orbital, you get more stable mixing, stabler mixing. Stabler is not a word, but we're going to pretend it is because it's faster to write than more stable. Stabler mixing if the starting orbitals that you mix together are closer in energy. And this actually comes out of the math in MO theory. I did the math at least in a crude and sort of clunky way when I was teaching that physical organic chemistry class. And you can demonstrate that two orbitals that are close in energy make a more stable bonding orbital than two orbitals that are far apart in energy. Okay? Suppose this is hydrogen and fluorine. They're from the same row of the periodic table. Their atomic orbitals are similar in energy. You get a very strong, a reasonably strong bond. In contrast, if this is H and this is I, those valence orbitals start out at a higher energy level, and so the bond you make is weaker. All right. Anything else we need to say there? So in terms of rationalizing pKa information, when thinking about things that have different sizes, where the atom that holds the charge varies in size, you're not going to worry about electronegativity anymore because that will lead you to the wrong conclusion. It's the size and the spreading out of electron density on the larger atom that matters, as well as the fact that the mixing between orbitals, valence orbitals of different rows of the periodic table is not as efficient and is not as stabilizing. Let's see how well you've got it. Let's think about acidity in a strange context. Let's think about the acidity of water versus the acidity of hydrogen sulfide, rotten egg smell, versus hydrogen selenide. Selenium is one row down from sulfur. And I don't know if you can make hydrogen telluride, but maybe you can. Who knows? Let's just start there. Which do you rank as least acidic in this group? Okay, you say that's least acidic. Why? Because if I draw the conjugate base, I see that the negative charge that's left behind when water loses its proton is on oxygen, which is pretty electronegative. So what's the big deal? Go ahead. The size of the atom, right? And size means that the electrons are not held as tightly. They are spread out over larger space. They have lower kinetic energy. They're held further from the nucleus. And they don't experience the nucleus as tightly. And because they're spread out over a larger area of space, the electrons are actually stabilized. Okay?
Could we also say that because hydroxide is a strong base, water is a weak acid, and because selenium is a weak base, that hydrogen selenium would be a stronger acid and more?
Exactly, yes. So the question was, can we say if water is the least acidic, that hydroxide is the stronger base? Yes. And that if H2SE is the stronger acid, does that mean that HSE minus is the weaker base? Absolutely. So, and this maybe gives us a chance to point out something you may have heard in general chemistry. In general chemistry, I believe you made a big deal out of what the difference is between a strong acid and a weak acid. And you may have been taught that weak acids also have weak conjugate bases. but I'm telling you here that the weakest acids have the strongest conjugate bases. What's the deal? Well, we're just talking about weak and strong differently. For organic molecules, the weakest acids that we've encountered are going to be like hydrocarbons, where the pKa is like 50. And what that means is the deprotonated hydrocarbon is going to be crazy basic, crazy reactive. What about, okay, let's compare that to water, like we said, pKa of 16, OH minus. Water is, if you're comparing it to HCl, water is actually a weak acid, but you would have called hydroxide a fairly strong base. Well, strong relative to what? It's certainly not strong relative to the deprotonated hydrocarbon, but it's a lot stronger than Cl minus, like we talked about. So weak and strong is just relative, and you need to make sure that when you say something like that, you're usually comparing two things, and you got to have that comparison in mind. Acetic acid is often called a weak acid in general chemistry because its pKa is such that if you put it in neutral water, well, I believe in general chemistry you defined weak acids as being ones that are incompletely dissociated. Well, we've debunked the concept of dissociation, right? We've said that in water, actually, what goes on is that we have this equilibrium where the proton would get transferred to hydronium, and if we're to ask what the position of that equilibrium is, we find the acid on both sides of the equation, we compare their pKa's. Who is the strongest acid? Hydronium. So equilibrium is going to favor this side. So yes, acetic acid is weaker than hydronium, but it's way stronger than a hydrocarbon. All right? So it's a relative comparison. Compared to HCl, yes, acetic acid is a weak acid. So we're not going to make this distinction between weak acids and strong acids. That, and the statement from general chemistry that weak acids have weak conjugate bases only really works for things that are in that area of our pKa table. Because it is true that the counter ion or the conjugate base of acetic acid, it is true that this is not very basic, but it is also true that it is more basic than water. All right. So, yes, you can basically, yeah, take it to the bank in this class that stronger acids have weaker or more stable conjugate bases. Okay? Yes?
So in general chemistry, we learned like that. I think it's because we were learning like under the Arrhenius, like it was a different definition of acid and base strength. But when we memorized like the list of strong acids and strong bases, we have like potassium hydroxide or things like that. And so that's just going off the definition that a base is something that will readily give up a hydroxy group. And that's different from this because like in what you just showed us, like the hydroxy group's weaker than a deprotonated hydrocarbon.
That's right, that's right. So the question is really about how we've talked about bases in this class versus in general chemistry. You may have thought about bases in general chemistry as being things that generate hydroxide. Here we're talking about bases as molecules with high energy reactive electrons in a high energy orbital, molecular orbital. And so yeah, I guess, is that the answer to your
Yeah, I
question?
guess I'm just asking like, not saying a lot, I guess, would it be better to think about it as Lewis acids and bases rather than like Bronsted-Lowry or other ways? Like, is it more
Okay.
beneficial to think of it like that?
Yeah, so the question is related to how should I think about acid-base chemistry and organic chemistry versus general chemistry. As far as as far as I know, the Bronsted-Lowry acid is a proton donor. And the Bronsted-Lowry base is a proton acceptor. But we've shown you that the reason HCl is a proton donor is because it has this low-lying sigma star into which it can accept electrons. So Bronsted-Lowry acids are and have to be Lewis acids. Okay? And that's what I mean by saying that we no longer think of HCl as, oh, I'm donating a proton, I'm so altruistic. No, it does lose its proton, but because somebody attacks it. All right? This stuff maybe happens in the gas phase, which is great, but none of us exist in a vacuum right now, and most of the organic chemistry we're interested in is in solution and in water in many cases. So we're going to be tied very closely to this relationship between Lewis acids and Bronsted-Lowry acids. And similarly, the reason a base can accept a proton is because it has high energy electrons that are going to remove that proton. So we're going to keep very closely tied Lewis base, Bronsted-Lowry base, Lewis acid, Bronsted-Lowry acid. Now you alluded to an Arrhenius acid. I actually don't even remember what that means, so sorry. Let's see, maybe now's a good time to pause and ask, is there anything in the chat that's coming up that I should address? Wait for it. No? Okay. All right. So we've talked about electronegativity as one reason why something might be more acidic than another. We've talked about spreading out electron density as a reason why something might be more acidic than something else. I want to give you another example of electronegativity and another example of spreading out electron density. So I've mentioned how methane is terribly not acidic with a pKa of 50. But if you ask about a proton on an sp2 hybridized atom, the pKa is 40. Still crazy not acidic, but 10 billion times more acidic than the methane was. And if you instead introduce a triple bond and then ask how acidic is that proton there, boy, the acidity starts to get down where it becomes reasonable to consider in some organic reactions. So why the difference of 10 orders of magnitude when going from methane to the alkene, and then why an additional 15 orders of magnitude going from the alkene to the alkyne? What do you notice about the atom that has the charge in the conjugate base? It's all carbon, so we don't have a difference in atoms. Why should one carbon better tolerate a negative charge than another? Well, whenever we've thought of carbon tolerating a negative charge better, we've thought about, well, lone pairs must be more stable here and less stable there. So start with that. Why do you think the lone pair electrons on the deprotonated alkyne are more stable than the ones on the deprotonated alkane? Got anything? Yeah.
I have no idea if this is right, but I guess since carbon is more electronegative than hydrogen, then it would have more of the electron density in that bond with the carbon-hydrogen bond, but since it's bonded to another carbon there, then maybe the electron density would be more stable between the two.
Okay. So you're thinking about the fact that over here I've got another carbon, whereas with methane I don't. Okay, I should have foreseen that potential complication. So I am altering the deal. Pray I don't alter it any further. I actually have a full-on Darth Vader costume. So if you go on my YouTube channel, actually, and scroll down, you can see a video that me and Dr. Michaelis did in his 351 class last semester for Halloween. I won't describe it any more than that, but it was awesome. And the production value was way higher than it was the previous year. We've gotten better as we've done it. I still almost caught on fire, which is scary, but what? Wait, no, we could watch it now, but we won't. No, we won't. Go ahead.
I was thinking maybe it had something to do with the pi bonds.
Okay.
Pi bonds are distributing the electronegativity of the electrons.
Okay. You do have pi bonds here. Are those involved? They are a factor, though it's more an issue of what the presence of those bonds tells you about the carbon itself. Let me give you a hint. What is there? Oh, go ahead.
Can I revise myself? My new guess is because the hybridized orbitals, if we look at the first one, then it's an sp3.
Okay.
Because it only has single bonds, and the other one's an sp orbital. And we know that the p orbitals are more like unstable.
Okay.
And so when it has more p character than the one stable.
All right, good. So let me restate that for those of you playing along at home. We see a difference in hybridization for the atom that bears the negative charge in the conjugate base. For the alkane in the conjugate base, the atom is sp3 hybridized. And that means that that lone pair is going to be in an sp3 orbital. Similarly, the lone pair on the deprotonated alkene is going to be in an sp2 orbital, and the lone pair on the sp hybridized carbon is going to be in an sp orbital. Now, you mentioned that there's a difference in energy depending on what the hybridization is. Where does that come from? How do you know that? Just for the unhybridized orbitals, if I'm P versus S, go ahead.
I know that s orbitals are more stable because of how they interact with the nucleus. And p orbital has that node in the middle.
Okay, good. P orbital has a node at the nucleus. Whereas the s orbital has substantial electron density at the nucleus. It's hard to illustrate this way. Let's just make a graph of, here is distance from the nucleus in whatever direction, and this is wave function. The wave function is positive and has a large value, max value at the nucleus in a 1s orbital. For a 2s orbital, there's a node at a certain radius, and then we tail off from there. It's like there's a node, not plane, but a sphere. That issue really isn't that important. The key is that the wave function has a positive value, has a finite value at the nucleus, meaning that an electron in an s orbital experiences the nucleus more than an electron in a p orbital. So let's just sort of think about distance from the nucleus along this axis that I drew for the p orbital. On one side it's positive, on the other side it's negative, but at the nucleus wave function equals 0. So an electron in a p orbital experiences the nucleus less than an electron in an s orbital. So the s orbital is lower in energy. The same is true for the exact same reasons with hybrid orbitals. sp orbitals are lower than sp2, which are lower than sp3. Why? Because sp is 50% s orbital and only 50% p, whereas sp2 is 33% s and sp3 is only 25% s. So we'll see that for hybrid orbitals, the more s character you have, the more stable you are, the lower in energy you are. So it makes sense that the conjugate base here with the lone pairs in an sp orbital is lower in energy than it would be for the conjugate base of our alkane, which is held in a higher energy sp3 orbital. Has to do with distance from the nucleus. Has to do with how much of the nucleus the electrons experience. And in that way, we can think of sp hybridized carbons as being more electronegative than, say, sp3 hybridized carbons. You can think of carbons with more, orbitals with more s character as being more electronegative. Because remember what electronegativity means in the first place. It means the energy of that atomic orbital. The more electronegative you are, the lower in energy that orbital is. So sp carbons are more electronegative than sp3 carbons. So, and you can use that to rationalize the difference. It's hard to think of more difficult questions I could ask you about this, because now that I've told you the answer, it's hard to think about how you might probe your understanding of this at any deeper level of detail. But we will see alkynes, we will see that this pKa for the alkyne is low enough to be relevant for some physiological reactions. Or, I'm sorry, not physiological, but for some organic reactions that we will encounter. What I will leave you with is the following acid-base equilibrium. And I want you to go look up pKa information, and I want you to figure out, and it shouldn't be too hard, I want you to figure out which side of the equation would be preferred at equilibrium, which is the same way as asking who loses their proton, which is the same way as asking is the deprotonated alkyne strong enough of a base to remove a proton from ammonia. Okay, so take that, see what you can get, and we'll see you on Monday.